Hello everyone, welcome back to my channel. Today let's go over a medium level question that I just solved on my own. So I'm super happy about this and I'm very glad that I was able to come up with my own solution to this question without any assistance. So let's go over it and let me show you how I did it. So this is question 2684, maximum number of moves in a grid. So you're given this matrix and all of them have positive integers. And basically what you want to do is from each cell, you can move either left, straight down, or down to the right, as you can see from these. And then you just want to return from each cell what is the maximum number of moves you can perform, with the caveat that the cell that you move to has to be of a strictly bigger value than the current cell. Okay, so let's do exactly that. So let's go through every single cell from rows top to bottom, left to right, so like this. And also notice that you can only start with a cell in the first column, so that actually makes it a lot easier, because what we can do is just run a DFS on each cell in the first column, right? So we don't even need to explore the rest of the grid. So let's just create a DFS with X, Y, and stack. And we're just going to keep appending to the stack as long as the current element is bigger than whatever's at the top of the stack, right? So, and then obviously we need to do our boundary checks. So like this. So if X is out of bounds, or the columns are out of bounds, then we return. Otherwise, if nothing is in the stack, then we can go ahead and append grid X, Y. And again, we're going to want to explore X plus 1, Y plus 1. And then also down to the left, row plus 1, column plus 1, row minus 1, column plus 1, and then row, column plus 1. So plus 1, minus 1, normal X. And then here, otherwise, if grid XY is less than or equal to stack -1, then we can just return. Otherwise, we're going to append grid XY because the current value is bigger than whatever's at the rightmost, the rear of the stack. Okay, or here. And then at the end, we can just go ahead and take the maximum of the length of stack itself, -1, right? Because if you can see, we don't have to count the current element. We just want to count how many moves we can make. You aren't moving from the cell you're starting from. So by that logic, that is length of stack -1. And since we're trying to maximize something, just throw a negative infinity in there and then return self.answer at the end. Okay, let's run this. Submit it. Okay, wrong answer. So it looks like, well, first of all, after we're done with exploring all the cells, we have to backtrack. So we're going to see stack.pop. And what you'll find is this is a quadratic equation. So let me show you what I did to optimize it. So we're almost there. So what you can think of is, since these are 3 recursive calls, why not just apply caching? And obviously, because we're using a list, we can't use their metadata annotation, so why don't we just implement our own cache, right? So we want to cache the result at X and Y, which is just going to be the answer because that's the best results, maximum number of moves we can get, right? So why don't we just say, if this key exists in the dictionary, then just return X and Y. Otherwise, so we don't compute it again, right? That's the whole point of memoization. Let's save the results as self.answer so we don't have to recompute this entire recursive call, right? Okay, let's run this. Use this test case and submit it. And there you go. Passes all test cases. So again, I'm super happy that I was able to come up with my own solution to this question without any assistance and solve it completely on my own. So that's it for this video, and thank you for watching.